Hello and welcome to Intro to Astronomy at OTC. This is the book Cosmic Perspectives, and we're going to look today at Chapter 1's lecture on a modern view of the universe. Well, here's a nice picture from the Hubble Space Telescope, and this is one of the Hubble Space Telescope deep fields, they call this. This is an image that's probably about 10 days in length of exposure. Now, the Hubble telescope orbits the Earth every 92 minutes, so it can only look at the part of the sky it's looking at for about half that time when it's on the other side of the Earth. These galaxies could be as far away as 10 billion light years or more. So our goals for learning in this: what is our place in the universe and how big is the universe? I'll give you a hint, it is very big. 13.7 billion light years across. So we start off with the Earth. We know the Earth is one of 8 planets in the solar system. The solar system is just one of 200 billion stars in the Milky Way galaxy. The Milky Way galaxy is just one of 24 galaxies in what we call the local group. And then we belong to a supercluster of galaxies that may be millions and billions of galaxies, each with 200 billion stars. So here's our source of life on the Earth. This is the Sun. And of course the Sun is a star, and a star is a large glowing ball of gas that generates heat and light through nuclear fusion in its core. The surface temperature of the Sun is about 11,000 degrees Fahrenheit, but inside the core it can be as high as 20 million degrees. Then we know we have planets. Planets are a moderately large object that orbits a star. It shines by reflected light, and planets may be rocky, like the Earth, icy, like Neptune, or gaseous in composition, like Jupiter. And then we have satellites. We also may know these as moons. So these are natural satellites, and a satellite or a moon is an object that orbits a planet. And here's a picture of Ganymede, which orbits Jupiter, one of the large Galilean moons. And then we have some kind of leftover stuff in the universe. And so one of these is asteroids, a relatively small and rocky object that orbits a star. Some of these orbit planets like the Earth. Most asteroids are found between Mars and Jupiter in the asteroid belt. And we have spent a number of spacecraft to go to asteroids to check them out. One of my most favorite topics to discuss, and I'll share a picture with you of a comet, is indeed comets. Comets are relatively small. Maybe the nucleus is only 2 to 20 miles across. And they are filled with dirt and gas and dust, and they orbit stars. And there are 2 places that comets can come from. They can either come by pretty close to us. By pretty close I mean out past Neptune and Pluto in what's called the Kuiper belt, or they can come from many million, trillions and trillions of miles away in what we call the Oort cloud. And so everything that makes up the stuff that goes around the Sun we call a solar system, and that includes the Sun, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, dwarf planets like Ceres and Pluto. Pluto is no longer a planet, at least for now. And comets and dust and asteroids and everything else. We get away from the solar system, we can look at what we call interstellar space. And we can find nebula. Nebula is Greek for cloud. And so here's a beautiful picture of the Orion Nebula. This is what's seen in the winter sky, and it's basically a cloud of gas and dust that's in interstellar space. So going even farther out now, we know that we live in the Milky Way galaxy, and it's got about 200 billion stars. So galaxies are these great islands of stars in space, all held together by gravity and orbiting a common center, and oftentimes at the center is a black hole. That's kind of the anchor point for that. Here is M31, the great galaxy in Andromeda. Very beautiful to see in the fall sky. And it's got a couple of its own little satellite galaxies, the Magellanic Clouds, and it's about twice the size of our galaxy, the Milky Way. So 400 billion stars, maybe even 2 black holes in the middle. And actually, our galaxy and the Andromeda Galaxy are actually coming together not anytime soon. It's going to be hundreds of billions of years from now, so we won't be around to see it, but we're closely going together. And then we go out to everything, the universe, the sum total of all matter and energy, everything within and between all galaxies. So let's take a look at some time scales. Light travels very fast, 300,000 kilometers per second. Put that in perspective, you might understand as miles per hour. It's about 186,000 miles per second. So a light ray can actually circle the Earth 7 times in 1 second. To get to the moon, light takes just 1 second. To get to the sun, light takes 8.5 minutes. So when you look at the sun, it is actually, that's how you see it 8 minutes ago. That light took 8 minutes to get here, so we don't see it in real time. We saw it as it was 8 minutes ago when it left the sun. One of the nearest stars to us is Sirius, and it is 8 years away, or we call it 8 light years. Light year is a scale of how far something travels in a year at the speed of light. It's not a time, it's a distance. And if you send a beam of light to the Andromeda Galaxy, which is kind of next door to us, it's 2.5 million light years away. So you look at the Andromeda Galaxy in the fall sky, you're looking at that galaxy as it were 2.5 million years ago. So the farther back we look in distance, the further back in time we are. So we see the Orion Nebula here. This is a winter constellation, a very big winter constellation. And this is how it looked 1,500 years ago, because it is 1,500 light years away. And so we're seeing ancient light. Those stars may not even be there anymore. So here's what the Andromeda Galaxy looked 2.5 million years ago. And the question is, when will we be able to see what it looks like now? Well, that'll take another 2.5 billion years. So here's the definition of a light year. It's the distance light can travel in just 1 year, and that is about 10 trillion kilometers and 6 trillion miles, which is a long way, folks. At even greater distances, we see objects as they were when the universe was much younger. We have now taken pictures of galaxies when the universe was only 500 million years old, which was 13 billion years ago. Pretty interesting. So we can look at this calculation here. I'm not going to go through it, but we can convert a light year into seconds and minutes and how fast it goes. Can we see the entire universe? Actually, no, we can't. There's a lot of dust in the universe. Dust and gas makes up the starlight we see. But the last, roughly 500 million light years of the universe, the very edge of time, is opaque to us. That early epoch of the universe is not clear for us to see through it. So it's kind of like a brick wall. So what is our place in the universe? We know the Earth is part of the solar system, which is the Milky Way galaxy, which is a member of a local group of 24 galaxies in the local supercluster, which has millions of galaxies. So if we were to take a scale of the solar system and put it on a 1 to 10 billion scale, the sun would be the size of a large grapefruit. Earth would be the size of a ballpoint pen, 15 meters away. So how big is the Milky Way galaxy? Well, the Milky Way, they say 100 billion, I say 200 billion. We don't know. We haven't paid a grad student yet to count them all yet. Haven't found one to do that job. Well, on the same scale, how big is the Milky Way? I can tell you the Milky Way is 100,000 light years across. So a star on one edge sends its light beams to the other edge of just our galaxy, it takes 100,000 years for that light to reach there. So our galaxy, the Milky Way, which is kind of a big galaxy, is one of just 100 billion galaxies. And, you know, when you take 100 billion galaxies times 200 billion stars, you get a really, really large number. There are as many stars in the universe as there are grains of sand on all of Earth's beaches. That's a good way of looking at it. There's a famous video that's been made a long time ago and been remade recently called the Powers of 10 video. And so we're going to take a look at how big the universe is in steps of powers of 10. So every time we move out, we're going to zoom out a factor of 10. Let's see if we can do this. How big is the universe? The distances between planets are huge compared to their sizes. On a scale of 1 to 10 billion, Earth is the size of a ballpoint and the Sun is 15 meters away. On the same scale, the stars are thousands of kilometers or miles away. It would take more than 3,000 years to count the stars in the Milky Way galaxy alone at a rate of 1 per second. And they are spread across 100,000 light years, as I mentioned before. The observable universe is 14 billion light years in radius and contains over 100 billion galaxies with 200 billion stars each. And that's a very large number. So how did we come to be, and how do our lifetimes compare to the age of the universe? Let's look at that. We're going to look at the scale of the universe on a scale of a calendar year. So we're going to crunch the whole 14 billion years of history of the universe into just 1 year. We know that the matter in our bodies came from the Big Bang, which is this infinitely small, infinitely hot point that started to expand 13.7 billion years ago. And that Big Bang produced hydrogen and helium. All other elements that were constructed from hydrogen and helium in stars and then recycled into new star systems, including our solar system. And here's a point I want to make. Our universe is mostly hydrogen and helium, but yet we have calcium and iron in our bodies. That stuff came from the insides of massive stars that exploded as what we call a supernova explosion and got dispersed through space. So, you know, the calcium in your bones and the iron in your blood, that all came from exploding stars. And so we call that, we're made up of stardust. Stardust. How do our lifetimes compare to the age of the universe? On a cosmic calendar that compresses the history of the universe into 1 year, human civilization is just a few seconds old, and a human lifetime is just a fraction of that second, December 31st. So now let's change to how the Earth is moving through space and how do galaxies move within the universe. Contrary to our perception, we are not sitting still. We are moving with Earth in several ways and at surprisingly fast speeds. One of these motions is rotation, and that happens every 24 hours. The Earth rotates along its axis. We know that the Earth also orbits the Sun. We call that revolution. So don't get rotation and revolution mixed up. Revolution goes around something else. Now, at this point, let's make a definition of a very, very important unit concept in astronomy, and that is the AU. That stands for astronomical unit, and it is defined as the average distance between the Earth and the Sun. We vary our distance in different seasons to the Sun. We're actually closer to the Sun in winter, but the light rays hit us indirectly and we're cold. But 93 million miles, 150 million kilometers, that's 1 AU. And we use AUs to talk about stuff within our solar system. The Earth's axis is tilted 23.5 degrees, and currently the North Pole of it points to the North Star, which we call Polaris at this time, and that changes over time as well. Well, we also know that our Sun is actually in an arm of the Milky Way galaxy, And the Milky Way galaxy is rotating as well around a common point, maybe a black hole. And that takes 230 million years for the Milky Way galaxy to rotate once. 230 million years. We also know that the Milky Way's light comes from a disk and a bulge. And there is dust in the galaxy. You can see here a dark band going through the middle, and that is dust. Dust and gas is the blue stuff, and that makes up stars. So how do galaxies move within the universe? In 1929, an astronomer named Edwin Hubble, who, if you're familiar with the Ozarks at all, you might know that he was born in Marshfield, Missouri, just 25 miles up I-44 from Springfield's campus. And he discovered that the universe was expanding, and so it's Hubble's law of expanding universe. And you can think of this as like a loaf of raisin bread. As you put the bread in the oven, the bread expands and cooks, and all the galaxies, the raisins, kind of expand along with it. So everything's expanding away from each other in the most part. So Hubble, and by the way, there is a monument on the Marshfield Town Square. It's a 1/3 scale replica of the Hubble telescope. If you've never seen it, you should go by the town square and see it. All galaxies outside of our local group of 24 galaxies are moving away from us. The more distant the galaxy, the faster it is racing away, and we call that Hubble's law. So if the galaxy is very far away, it's moving very fast away from us. And the conclusion is we live in an expanding universe. So here's the motions. Earth rotates on its axis. Earth orbits the sun pretty fast. The solar system moves around other stars pretty fast. The Milky Way rotates pretty fast, 800,000 kilometers an hour. The Milky Way moves through our local group, and the universe expands. The Earth rotates on its axis once a day, 24 hours, and orbits the sun at a distance of 1 AU, 1 astronomical unit, 93 million miles, as we have defined. The stars in the local neighborhood move randomly relative to one another and orbit the center of the Milky Way in about 230 million years. A lot of numbers here. So how do galaxies move within the universe? All galaxies beyond the local group are moving away from us with the expansion of the universe at set speed, and the more distant the galaxy is, the faster that speed is, Hubble's law. So how has the study of astronomy affected human history? Why are we in this class learning this anyways? How does it affect us? There was a time early on, and we'll discuss later, that pre-1600s AD, we thought that the Earth was the center of everything. That was called the Ptolemaic model. That was ancient thought. And then observations started to come into play. In 1609, Galileo used a telescope that was invented by Italian lens makers to look at the solar system. After that, Nicholas Copernicus came around and said that the revolution showed that the Earth was not the center of the universe. And again, we'll cover this in a future chapter. The study of planetary motion led to Isaac Newton's laws of motion and gravity, which we'll also cover in chapter 4. Newton's laws laid the foundation of the Industrial Revolution, and the modern discoveries are continuing to expand our cosmic perspective. So throughout history, astronomy has provided an expanded perspective on Earth that has grown hand in hand with social and technological developments.